Good morning, everyone. My name is Wei Bao. I'm from University of Sydney. So today I'm going to present my paper. It's about this probabilistic caching and recaching in mobile networks. So at the beginning, I need to give you a quick introduction. So nowadays, this caching in mobile networks is becoming more and more useful. This is because we have more and more data-intensive applications like multimedia applications and AR and games. Okay. However, the mobile devices have limited capacity and also may experience limited network capacity. So in these scenarios, caching could be very useful because they allow this content reuse. So when we want some files or some contents, we may directly download from the peers instead of directly downloading from the network. So in our work, we are motivated to answer some questions. The first question is which files should we cache? So this is because we have limited capacity. So we want to select the best files so that we can maximize the overall utility. And also, so because the popularity of the files could change, so in this case, we need to replace those files. So the other question is how can we smartly replace the files? Okay, so here a very important thing is that we want to minimize the number of files we are going to replace. Okay, so here comes the outline of the solutions. Okay, so first I need to introduce a previous work. It's about this probabilistic file caching policy. This is very important. This is done by previous work, but it's really important, so I need to have a brief review of it. For this PFC policy, so given those caching probabilities, okay, so how can we realize those caching probabilities? However, this PFC policy doesn't answer two questions. The first one is if the caching probabilities change, how can we update? The second one is how can we optimize those caching probabilities? Okay, and these two questions are answered by our proposed policies called this PFR, Probabilistic File Recaching Policy, and this OPCR, Optimal Probabilistic Caching and Requesting Policy. So how can we use those policies? Okay, so let's see this system. Okay, so this is a timeline. Okay, and the system starts here, and at this time instances, okay, the popularity changes. Okay, and then we use this OPCR policy. So that means given the popularity, okay, so we determine this optimal caching probabilities of the files. And then at this time instance, okay, because we need to realize those caching probabilities. So in that case, we need to use this PFC policy so that we realize those caching probabilities. At this time instances, okay, so we need to realize those updated caching probabilities. So in this case, and we need to use our proposed PFR to realize those updated caching probabilities. Okay, so now I need to have a brief review of this PFC policy, which is proposed by the previous paper. Okay, here, and this is a very smart policy. So basically, suppose we have n files in the library. Okay, and this F denotes the set of all files, and we want to cache exact k files, and with this caching probability, the ith files caching probability is qi. Okay, so and given the summation of these probabilities is k. Okay, so given those probabilities, how can we cache the files? Okay, so here the challenge is that we need to cache exact k files. Okay, so in that case we cannot to do that independently for every file, because if we do that, and we may not guarantee that we exactly cache k files. So in that case, we need to make one decision for all files at the same time. Okay. So in order to demonstrate this policy, I need to give you an example. Okay. So suppose we have we want to cache 4 out of 8 files k is equal to 4 and n is equal to 8, and the probabilities are these ones. Okay, and then what do we do? Okay, so first we draw like 4 bars. Okay, the bars are from 0 to 1, and we divide the 4 bars into 8 regions. Okay, so the 4 corresponding to k, and this 8 corresponds to this the n. Okay, and then like, so first like we set this 0.8 corresponding to this probability. Okay, and then we allocate the next 0.8 corresponding to the next 0.8. But here, because like the first bar cannot cover the 0.8, so here we have 0.2, and here we have 0.6. And then we cover the next 0.6, okay, so which covers here, and then 0.5, 0.5, 0.4, 0.3, and 0.1, okay? And then what do? We randomly, so those are corresponding to those probabilities. Then we randomly generate this vertical line, okay? And this vertical line is uniformly distributed in 0 and 1, okay? And then this line passes like 1, 2, 4, and 6. So in this case, and we will store like 1, 2, 4, 6, okay? And because like this vertical line is randomly generated, okay? So say like if it's here, okay, so we are going to cache 2, 3, 5, and 7. So this is very smart because like we exactly cache k files, and actually say because like the length of this one is 0.8, and this is uniformly distributed from like 0 to 1. So basically this is cached with the probability 0.8. So by doing so, okay, so we can realize those probabilities, and like we can exactly cache k files. So this is done by the previous work, but this like a PFC policy doesn't answer the question what happens like if the probabilities change. So this is done by our proposed PFR policy. So here we consider these probabilities are changed from like Q to Q prime, okay, and this will be caused by the popularity change, which will be introduced later. So one straightforward way and one naive way just to rerun the PFC, but this is where it's not ideal. Say like we have very small probability change, say like here, okay? So this probability is increased by 1 over like 10,000, and this probability is decreased by 1 over 10,000, okay? And before the probability change, okay, so 1, 2, 4, 6 are cached. But now if we rerun the PFC, say like if the vertical line is generated here, then we need to like cache 2, 3, 5, 7. So basically 3 files should be replaced. So even a tiny probability change may lead to this 3 file change. So this is really bad. So we want to address this issue. So we want to minimize the number of files to be replaced. Okay. So we propose this PFR policy. So in order to introduce this policy, still I need to give you these examples. Okay. So for in this example, suppose like we have k equals to 2 and n equals to 5. And now suppose like files number 3 and file number 5 are cached before the probability change. So in this case, 3 and 5 are probabilistically opt out, and the rest of files 1, 2, 4 are probabilistically opt in. Okay, so we construct this opt out bars and opt in bars. Okay, so in this case, okay, so we can see the 3 and the 5 covers this opt out bars, and this 1, 2, 4 covers this opt in bars, and these values are these opt out probabilities and opt in probabilities. Okay, so in this example, suppose like we generate, so still we randomly generate this vertical line. So suppose the line is here. Then in this situation, like files 3 and 4 are opt out, and the files 3 and 5 are opt out, and the 1 and 4 are opt in. And suppose like this vertical line is generated here. So file 5 is opt out, and file 2 is opt in. Okay, so basically we can see, and by doing so, okay, so we randomly opt out some files and randomly opt in some files, and those values correspond to this opt-out probability and opt-in probability. So the next question is that how can we design those opt-out and opt-in probabilities? This is very important. So suppose like this xi is the opt-out probability of the ith file, and zi is just a stay-in probability, and the yi is the opt-in probability of the ith file. Okay, so in order to realize this new cache probability qi prime, okay, so we need to satisfy quite a few important like conditions. The first one is just based on the total probability formula. So here, the new cached probability is equal to the cached probability times the probability is not like replaced plus the probability is not in the cache times the probability is opt-in. This is just a formal total probability. And then we have this one. So this is the number of opt-out files equals to the number of opt-in files. This is very important because let's go back to this figure, okay? So here we need to make sure that if like one file is opt-out, then one file is opt-in. Like if two files are opt-out, then like two files are opt-in. So in this case, we can see the sum of these opt-out probabilities equals to the sum of these opt-in probabilities. So in this case, no matter where this vertical line is, and actually we have the same number of files. Okay. So in that case, and we have the sum of these opt-out probabilities equals to the sum of opt-in probabilities. And also here, in this situation, we only have like one situation, okay? So just like 3 and 5 are cached before the probability change. But in reality, we may have arbitrary 2 out of 5 files may be cached before this probability change. So in that case, and we need to consider like all these possibilities. Any k out of these n files could be cached before the probability change. So in that case, we need to consider this n choose k situations. So this equation actually indicates like n choose k like equations. Okay. So in order to solve like those equation group, okay, so we have this corresponds to n equations and this corresponds to like n choose k equations. But we only have like 2n like unknown variables. But the good thing is that there's like linear dependency. So actually we can still find this closed form solution to the previous like equations. Okay. And then we have like, this is the final solution, okay, so which is in closed form. Okay, and so by doing so, okay, so this is very important because we get this insensitivity to minor variance. So that means if like Q is approaching to Q prime, this xi and the yi values will approach to 0. Okay, this is very useful because like if like the probability doesn't change much, okay, and we don't replace many files, okay. And then we can see, okay, so if like Q approaches to Q prime and this is 1, and so this is 1, this is 0. So this is very useful because if there's only a small change in the probability, and we only replace very few files. Okay, so finally, I also need to discuss like how can we determine this optimal like caching probabilities. Okay, so here we need to make some other assumptions. Okay, so here like we know the popularity of the files. Okay, so the popularity is defined as this probability that the file is like requested, and we want to optimize the expected utility of the user. So if like so then we have this request model, okay, and so if I don't have the file and I'm going to like ask for my closest peer, and if he doesn't have, I'm going to ask for the second closest peer. If he has, and I'm going to download it. And if he doesn't have, I'm going to keep asking, and until I ask for the else closest peer. If he doesn't have either, then like I'm going to download from this server. Okay. Here, this L is also the value we want to optimize. So Then we want to define this RL, which is a utility if like we are successful at the else pair, and R0 is a utility if like I have already had a file, and this S is a utility if like the request is from the server. And we want to define this, given the popularity of the files, we want to define this cache probability Q and also the request limit, which is L the farthest pair I'm going to request for. Okay, and we want to maximize the expected overall utility of the user. So finally, we arrive this optimization problem. Okay, we want to optimize the expected overall utility under these constraints. This is a non-convex optimization, but first we want to find another way to find the optimal solution. So first we find like L, so L star. So if L star is like satisfied this condition, okay, then L star is an optimal solution. And given L star, the rest problem to solve Q is a standard convex optimization problem. Then like we can just use standard like convex optimization methods to like solve the problem. So that's all for the second part. Okay, so basically that we answer the question: how can we determine the optimal probabilities? Okay, so finally, and we use like simulations and we use this prototype to test like our schemes. So we use like we build this Android app. Like we have like a game with 11 game levels. So we need to download the game level before playing. The file size of each game level is 5 MB. And we compare our scheme with this like traditional schemes like highest popularity first, and equal probabilistic caching, and least recently used and least frequently used, and random replacement. So this figure shows the performance of our testbed. Okay, so we can see like under like different situations, and our scheme is better than all of the others. And also we use like simulations to test like when the case and n values are much larger. Okay, and in this comparison, we can see that the performance of our proposed scheme is much better than all the others. And also, like we want to test the PFR, and we compare it with the PFC. So here PFCR means like each time we rerun the PFC, the probabilistic file caching scheme, we rerun that. So we compare the number of files replaced. So we can see like our PFR replaced like much fewer files compared with this PFCR. And also like we compare this performance with the traditional schemes. Okay, we compare the replacement rate, which is defined as the expected number of files replaced per request. And this x-axis shows the frequency of this popularity update. So here we can see like this means like we have like one popularity update every 50 requests. So that means like the update is not very frequent, it's very infrequent. So we can see like these are traditional schemes and they are not relevant to this update frequency because they don't care. They don't care this whether there's a popularity update. But for our PFR, because like we only update, we only replace when there's like popularity like change. So in that case, we can see the number of requests replaced files will be decreased, okay, for the PFR policy. Okay, so finally I need to make a quick summary. So we consider this probabilistic caching and recaching policy. So we propose this probabilistic file recaching policy. Like we can handle like n choose k possibilities, and also it's insensitive to this minor variance. So if the probability doesn't change much, and actually we don't replace many files. And also we propose this OPCR policy so that we can determine this optimal caching probabilities. And finally, we use like experiments and simulations to test our policies. Okay, so that's all for my presentation. Thank you very much.